right, our next topic is going to be on multi-language smart contract development. And so this is about smart contracts in any language and how we onboard the next million developers onto Web3. So please join me in welcoming to the stage Professor of Computer Science at the University of Illinois and founder of Pi Squared, Grigore Rosu.
Hello, I am Grigore, the founder and CEO of Pi Squared, and our mission is to bring the next million developers to Web3. What is the problem that we try to address? Fragmentation. There is a lot of fragmentation in Web3 at all levels. Programming languages, lots of programming languages, lots of applications fighting with each other to gain more users or steal users from each other, user experience, and so on and so forth. Fragmentation could be one of the main reasons why Web3 doesn't have more developers. What is our solution at Pi Squared? If there is one word to go home with from this presentation, is universality. On 3 different dimensions. First, universality with respect to programming languages. Pi Squared offers a framework in which you can use any programming language to write smart contracts. Universality with respect to verifiability and proof mechanisms. So Pi Squared allows you to settle anything that is provably true. We call these claims. And universality with respect to consensus, distributed consensus, that allows various consensus mechanisms to coexist. Our stack, universality stack, includes 3 major components: ULM, USL, and UCP. ULM, think of it as the universal language machine, that's where the initials come from, the universal language machine, which is what allows you to write smart contracts in any programming languages. Even plug and play your programming language. Say you want to invent a new language, my language 1.0, then import my language 1.0, and now, voila, you can write smart contracts in your language. That's how easy it is to add new languages. And if you are interested in seeing this in a demo, we invite you tomorrow in the Boodle event, where we have a workshop, a 1-hour workshop. I'll talk more about that. USL is the universal settlement layer, which allows you to generate proofs of execution and settle such executions once and for all across different programming languages. And proofs can be not only ZK proofs. Typically in the Web3 space, when we say proofs, everybody understands ZK proof. No, they can be mathematical proofs as well. As I said, a claim is everything that can be proved rigorously and verifiably to be true. Any of these can be settled using the USL. And UCP is our consensus protocol, which is extremely scalable. Basically, you can settle and agree on a claim with just 1 round trip between a client and the verifier. You cannot do any faster than that. What does this really mean in terms of our goal to bring millions of developers to Web3? Well, ULM allows every developer in any programming language out there to become a Web3 developer. They no longer have to learn obscure and honestly badly designed programming languages only to enter the Web3 space. They can use their favorite languages, Python, Rust, and so on. USL allows any applications out there, Web3 or Web2, to settle executions that they want to claim correct in other places, on blockchains or to other applications. So essentially, any correct execution, any execution of a program that you don't have or don't want to hide anything to the world, you can prove and settle once and for all on the USL. And UCP will allow us to achieve agreement or distributed consensus at the fastest possible speed, the speed of light, basically. And this will allow us to process billions of transactions which are independent, inherently, between different applications that do not necessarily interact with each other. Billions of such transactions which become claims, all of them to be agreed upon in parallel, as opposed to sequentially, one after another. And this is why we believe that the market opportunity for Pi² is huge, because we can extend the world of developers from 20, 30,000 that we have now in Web3 to essentially the entire universe of developers, including AI agents, because they may want, and they will have to in the future, that's my firm belief, prove what they do. If an AI inferencer infers something for me, I want to make sure that it's the right inference done. As I said, universality is the main message to take home from here. So instead of asking why universality, let's first very quickly explore why not, why we don't have universality currently in Web3. Why it is not as easy as said to have universality. Well, essentially, the programming language field is at least complex, very complex, probably one of the most complex fields in computer science, and certainly one of the oldest fields in computer science. And what we see in the blockchain, in the programming language space, is that we have lots of combinations between programming languages and tools for them. For example, you have Java, and then you have Java interpreters, and then you have Java program verifiers, Java compilers, or EVM, you have EVM interpreters, or EVM program verifiers. And all of this, every single arrow in this picture, is a whole system by itself, super complicated. Okay, take C. C and compilers, GCC, right, or ICC, or Clang, right? So dozens, maybe hundreds of man-year work in these tools. Okay? It's very hard to simply port all this to Web3. It's a huge effort that causes barriers for adoption, barriers for being universal with respect to programming languages. And then not to mention maintaining all these tools. You update Python from one version to the next, who updates all these tools? Maybe somebody updates an interpreter, because you need to have something at least. But how about the rest? So that's the problem. That's why we believe we don't have all programming languages right away from start in Web3. So what is our solution? Well, it's something that we've been working for more than 20 years by now. I proposed the K framework back in 2003 when I was a NASA scientist. And this is what the K framework does. It completely eliminates all those n² number of arrows and does the right thing, which is separate programming languages from tools for programming languages. Programming languages are defined, and we use the word define as opposed to implement, but you can also use implement if you want, once and for all, as a formal semantics. Anybody here heard of formal semantics? All right, formal semantics is the only way to talk about correctness, right? You hear lots of people talking about this program is correct. Correct to respect to what? You need a formal semantic, which is a mathematical definition of the programming language, to even be allowed to talk about correctness. Otherwise, the term correctness doesn't have any meaning, it's vaporware. Now, once you have a formal semantics, the K framework builds everything else for you. This approach is also called the correct by construction-ness approach, because there is nothing to prove correct. It is correct by the way we build. So it's the K framework that got to the level of maturity that we need in order to bring all programming languages to Web3. That's what fuels our technology. So this allows us to separate concerns between language design and tool implementations. As I said, it allows us to plug and play your programming language. And it's been worked at more than 20 years by my research lab at University of Illinois, where we invented it, but then also several companies use the K framework, mainly for formal verification. But it transcended that field. Now it can be used for execution as well, for proving execution as well. I know this is not a programming language class. All I want to convey here is that it is not rocket science to define a formal semantics of a programming language. This is a language that we'll demonstrate tomorrow in the Buidel event, if you can come. It's a very simple language, and this is everything you have to do to define that language mathematically. To the left, you have the syntax of the programming language. Like this is the syntax of if, then, else. If, the quotes, these are terminals, these are non-terminals. If, then, true. And also strict of one. That says the evaluation strategy. Evaluate this argument. Now, here you see the semantics. For the semantics, usually you have to define a configuration, saying like where everything is, all the semantic components, all the values, the state, maps, stacks, everything stays. And then rules. These rules, each of them captures a computational step, but they are very parametric. For example, these are the rules for if then else. Once the first argument evaluated, now we have two rules. One when the argument is 0. This is a C-like language. If 0, then you pick the second branch. This says I don't care what's there. And this says otherwise, pick the first one, provided that is different from 0. Same semantics I can see. And that's everything you have to do about a programming language. Students taking programming language design classes define languages much more complex than this as class projects. Languages like Java, C, Python, JavaScript, they have been defined by students as master theses or PhD theses or even class projects, some of them. So it is not very difficult to define these languages. But the benefit is immense because that's all you need about this language. You never need to worry about implementing an interpreter. You never need to worry about implementing a ZK VM for this language. You never need to worry about implementing a program verifier, symbolic execution engine, because all of this can be generated automatically, correct by construction. All right, which is the basis for what we do at PySquared. So maybe now it's time to tell you what PySquared comes from. Comes from proof of proof, and specifically from zero-knowledge proof of mathematical proof. And I will tell you a bit more. I know this figure is complex. Let's just look at the input and the output. The output is a zero-knowledge proof, same like in any zero-knowledge circuit, ZK VM. The input contains a program, execution environment, same like any ZK VM or ZK execution environment. What is different, though, is that the programming language is also an input. Okay? The ZK VM is not hardwired, built, crafted for one particular language. The programming language is input. And another thing which is in sharp contrast with existing ZK approaches is what's in the center. It's a mathematical proof. So what happens, the K framework does all the magic here and reduces computation to mathematical proof. Okay? That's another way to think of the K framework, or of a programming language semantic framework. It reduces mechanically, completely automatically, computation in said language to rigorous mathematical proof. And once you have the rigorous mathematical proof, you can check it. Because, by the way, mathematical proofs, like anything else, can be wrong. Okay? And many students cheat professors with wrong mathematical proofs, right? But if I have a proof checker to check the mathematical proof, I know that nobody cheated. I know that the proof is correct. And this is now what is done in the ZK world. A ZK circuit that has one simple job, which is to check the integrity of a mathematical proof. Much easier than implementing a ZK VM. But this gives you a ZK VM for any programming language and VM with one circuit only. Right? Have to rush a little bit. So what's the current status of this? We started our company 1 year ago, and our first job was to make K faster. Because when you hear all these mathematical proofs, correctness, correct by construction, the first thing that clicked in your mind, I'm pretty sure, was, but this must be dead slow. Right? Performance must be terrible. Well, it was 1 year ago. It was like 10x slower, 1,000% slower than GET for EVM, which was bad. Well, still good because it was absolutely provably correct, but bad in terms of performance. In 1 year, we improved the performance so that now it is faster than GET. It's 1.58 times faster than GET. Okay, so let me tell you what's going on here. Take an EVM program, run it with GET, and now run it with the K framework that produces under the hood the mathematical proof, because it's a prover. And this is faster than GET. So whoever tells you that formal semantics is slow, so don't use it, fight them back. They are wrong. Tell them, not anymore. Formal semantics now is fast. The other challenge was to demonstrate proof of proof. Does it even make sense? Can you even do ZK proof of mathematical proof? And our plan initially was to generate mathematical proofs and then use some ZK VMs to implement our circuit just to demonstrate that it works. What we've done in the meanwhile, we actually used 7 different ZK VMs. Because we used one, then we contacted the builders, and other builders heard of it, contacted us, and we ended up trying all the major ZK VMs. And there is a benchmark with almost 10,000 tests. Multiply this, 1,200 tests, but with 7 ZK VMs. It's one of the most comprehensive, actually, benchmark for ZK VMs this day. And all of these can be, they're all open source. Everything we do is open source, public. Read the white papers. Another thing we wanted to do was to take Ethereum transactions and settle them as claims on the USL to show that, yes, we can bring actually real transactions from Web3 into this world of mathematics and mathematical correctness. And we did a lot more than that, actually. And again, I invite you tomorrow to see demos of both USL and ULM. We integrated with Wormhole. So USL now can replace the guardians in Wormhole. Okay? And also with the pod protocol, a very recent protocol that promises also amazing performance. We'll talk about that tomorrow as well. And also ULM as a blockchain. Think of ULM as a blockchain which you can bring all programming languages, plug and play your language. We'll demonstrate it tomorrow as well. That was not planned, but it works beautifully. So strongly advise it to come tomorrow. With that, I'll remind you what ULM is. It brings all programming languages to Web3 correctly, efficiently. And we believe this could be the ultimate execution layer in Web3. Why compromise? Why pick other languages? Have to speed up. And let me actually say why this is interesting here in this particular context. Because we believe we can integrate this with Hedera. We believe we can bring all programming languages with Hedera by integrating Hedera with pi squared. And that will bring mathematical correctness. It will bring also a unified state model that will allow bringing new programming languages like Move, for example, which have a different storage model. Reduce overhead end-to-end because you can do ZK proofs. And also easy integration with off-chain applications because you can get proofs from those and then commit them on chain. With that, I thank you.